Good day, everyone. Today, we will be discussing about the magnetic fields. Magnetic fields are an essential part of nature and technology. But have you ever wondered where these fields come from? Magnetic fields are not just abstract concepts. They're caused by moving charges and specific materials. So, let's dive deeper into the key sources of magnetic fields. So, the first and most fundamental source of a magnetic field is a moving charge. When electric charges move, they create a magnetic field around them. This is the basis of electromagnetism. To explain further, consider a straight current carrying a wire. The flow of electrons in the wire generates a circular magnetic field around it. This can be visualized using the right hand rule. So point your thumb into the direction of the current. So this is the thumb and this is the current. And the fingers curl is the direction of the magnetic field. Next, we have magnetic materials. Some materials like iron, nickel, and cobalt have atoms with unpaired electrons. These unpaired electrons spin and create tiny magnetic fields. In most materials, these tiny fields cancel out because the spins are randomly aligned. But in magnetic materials, the spin can align in the same direction, forming a strong magnetic field. This alignment creates permanent magnets, which are used in everyday applications like speakers, motor, and compasses. The Earth's magnetic field, for example, is caused by the motion of molten iron and its outer core. A changing electric field is another source of magnetic fields. According to Maxwell's equation, when an electric field changes over time, it produces a magnetic field. This is the principle behind electromagnetic waves. For instance, radio waves, microwaves, and light all consist of oscillating electric and magnetic fields which propagate through space. This concept is fundamental to modern communication technologies such as Wi-Fi, mobile phones, and radio broadcasts.
In 1820, Sir Hans Christian Ørsted discovered the relationship between electricity and magnetism. Meanwhile, a French physicist named Sir André-Marie Ampere is nag-experiment pa siya during that time to learn more about the relationship between currents and magnetic fields. Sir Andre prepared two wires and he allowed the current to flow in one direction, and this is what happens. The wires attract to each other. After that, he allowed the current to flow but in opposite direction, and the wires repel to each other. Amazing, isn't it? In that experiment na gikonduct ni Sir Andre-Marie Ampere is nag-lead niya to discover the most important, the most fundamental law in electromagnetism and named after him, the Ampere's law. So ako nga explain unsay nahitabo sa experiment na Sir Andre-Marie Ampere katong duha ka wire. So for example, I have here a wire. So just imagine nga na current nga na-flow ani na wire. So, kanama siya current, it means maka-generate or maka-create siya of magnetic field na mag-circle around the wire. Like circle siya. Sir Andre realized that the stronger the current is flowing, the stronger the magnetic fields would be on that circle. The formula for Ampere's law is integral of B, which represents for the magnetic field, times cosine theta with respect to distance is equals to a magnetic field constant times enclosed current. This is the formula for the Ampere's law. So the B here, it represents the magnetic field. The cosine theta, it represents the angle between currents, or mean magnetic fields, with respect to distance is equals to magnetic field constant times the enclosed current. Let's go back to our diagram. So it shows a wire with a magnetic field surrounds. Imagine that there is a current flowing through the wire. So it's because there is current, it means it can generate magnetic fields. And because current is continuously flowing through the wire, it means it continuously produces magnetic fields, just like that. And the magnetic field that produced by the wire is parallel to the circle. We all know that cosine theta measures the angle between magnetic fields. And because it is parallel to the circle, it means the angle is 0. And cosine 0 is equals to 1. And it means we can eliminate the cosine theta in the equation. Notice that every part of the circle is equal in distance, so it means that B, or the magnetic field, is constant. So kay constant na siya, pwede siya ibutang in front sa integral. Here, all we need to do is figure out the integral of all points along the circle, which is equal to the circumference of the circle. In short, if atong i-apply ang Ampere's law along a straight wire, the total magnetic fields along a circle surrounding a wire is equal to B times 2 times pi times r. And B to pi r is equal to magnetic field constant and equals current. So the final formula for the Ampere's law is B is equals to magnetic field constant times enclosed current over 2 pi r. The equation is very important for Sir Andre when he's trying to figure out unsay nahitabo sa duha ka wires, why it ni-attract siya, and for what reason ngano ni-repel siya. About sa wires, sayon na siya sabton if mag-utilize ka og right-hand rule. So here, this is the wire, and this is my thumb. My thumb points to the direction of the current, while my fingers, it points to the direction of the magnetic field. In conclusion, the two wires repel and attract to each other. It's because of magnetic fields created by the current itself.
Today, we'll be talking about the Biot-Savart law, a fundamental concept in electromagnetism. So this law explains how electric current create magnetic fields, which is essential in understanding many real-world applications, like the motors, the MRI machines, and the electromagnets. But what is Biot-Savart law? So the Biot-Savart law provides a mathematical way to calculate the magnetic field produced at a point in space by a current-carrying conductor. So it's especially useful for analyzing magnetic fields generated by complex current configurations. So the law states that the magnetic field depends on the current, the distance from the point of observation, and the orientation of the current element. Of the Biot-Savart law, where dB stands for the infinitesimal magnetic field, I stands for the current, dl stands for the infinitesimal length of the wire, r stands for the unit vector pointing from the current element to the point where we measure the magnetic field, r stands for the distance from current element to interest, and this one, the permeability of the free space. Calculate the magnetic field at a point 1 meter away from an infinite long straight where carrying a current of 1 Wait, and here's the general formula, and we just simplify this to get this easiest formula. And now we will use this formula to answer this problem. So the given is the current is 5 amperes and the magnetic field are at point 1 meter away from the infinite long straight. So 4 pi times 10 to the power negative 7.5 over 2 pi times 1 is equal to 1 microtesla.
Hope you guys learned something from us today. Until next time, bye!